quickly. So a lot of you have heard this story, but not everyone, I imagine. So it started with a crazy idea around 2011, I think, and since that time, it's led to quite a number of PhD theses, and I can add one more on this, Gloria Meng, and lots of postdoctoral work and collaborations with many excellent scientists that are, I'm probably missing people here, but here are some of the, yes, I can see I just thought of someone I'm missing, but they're all on my slides. So it's kind of jump-started a bunch of work. I don't know how many of you know my history. I worked on incompressible fluid equations. You know, the famous Navier-Stokes Clay Math Prize problem is actually discussed in a book that I wrote with Andy Maida about, gosh, it's been a long time. I feel really old, 17 years, I guess. It came out in print. When I moved to UCLA, the impetus to move there was actually, I wanted to get into new areas of science. And one area that I had gotten into kind of through the back door, actually through the fluid equations, I was asked to look at a problem where some people were having trouble getting their hands around the theory behind an idea called image-in painting. And I said, yeah, you guys are actually trying to solve what looks like a variant of the Euler equations from incompressible fluid dynamics using the Navier-Stokes boundary conditions. And they were looking at me cross-eyed, like, what the heck are you talking about? And I said, well, you know, people have been developing numerical methods for computational fluid dynamics for about, I don't know, 30 years, so why don't we use some of those instead of what you're doing? And so that was my first paper in image processing. And that led to my eventual move to UCLA, where there was a big group working on image processing, image segmentation, which is a beautiful free boundary problem where you have an object like Pascal, okay? You have an object in the plane, and you yourself as a human can go look at it and take a pen and trace it out. But what you want to do is get a machine to do that automatically without any human in the loop. And so that is the segmentation problem. And of course it's very geometric, as you can imagine. So there were a number of papers in the literature. I learned about them. These are three of what I consider to be the highest impact papers on image segmentation. Other people may disagree with me, but I think these are three of the most, and in fact, the third one is really a derivative in some sense of the original Mumford-Shaw model here. All of them are in the form of an energy minimization problem. So what that means is you construct an energy functional, you minimize it, and hopefully that gives you a solution of the segmentation problem. So for example, here you have data F, and you are trying to find the objects that are in this energy. So there is a smooth version, a piecewise smooth version of F called U, which you don't know, and a curve gamma, which is separating the two smooth pieces, right? So you're allowing U to jump across gamma, but on either side of gamma, which is this, so away from gamma, right, you expect that there's some smoothness of U, so you have a penalty, an H1 penalty. You have an L2 penalty as a fit to the data, and the sort of hidden on the way over here on the side is perhaps the most important term up there, which is the length of the boundary. Okay, so you want to minimize the length of the boundary. That's where all the geometry is in this problem, is that term right there. So Terzopoulos said, you know, I want to solve this problem with a Lagrangian formulation where I'm going to take a curve, I'm going to parameterize it, and I'm going to move the curve around inside the image. So Terzopoulos said so minimizing the length of the curve with a simple parameterization, it's easier to do that by imposing some regularity like this. So here we have a parameter S for the curve, and you have the square of the first derivative and the square of the second derivative, the sum of which will bound the length of the curve. So you can think of this as, it's not directly minimizing the length of the curve, but it will certainly give you that effect. And all the information about the image, which is here in this term, is sort of hidden in this F term, and it's basically a force field that kind of pulls the curve into regions where there's a lot of change in the image, right? So that's kind of a mechanistic model. by Tertsopoulos. This has been used, this is also, I mean, you can look up the number of citations. It's huge, the Caswick and Tertsopoulos paper. Medical imaging is one area where there's a lot of papers using this model. Very easy to code up, easier than some of these other models. So in 2001, my colleagues from UCLA, Tony Chan and Luminita Vesse, said, hey, let's revisit Mumford-Cha with a very, very simple representation of the image. Rather than looking for piecewise smooth, how about looking for piecewise constant? So you're assuming, in this simple model here, you assume that your image is just two constants. So we're talking like Andy Warhol paintings, right? Two constants, only very simple, like black and white Andy Warhol, right? For people who know what that is, maybe I'm old, I don't know. So two constants, which you don't know, you have to find them, and the curve, right? Okay, so you define the constants and you define the curve, and if you take this model and plug it into Mumford-Cha, this term survives. There it is right down there, looking very innocuous by itself. This term is the gradient of the constant on each side of the curve, and the gradient of a constant is 0, right? So that term's gone. It vanishes. And then this is the least squares term, just turns into these two terms here. So that was their model, and they solved that using level set functions. And that paper also had a huge impact because you might think this is too simplistic. You can't represent an image by two constants, but we all know Andy Warhol did pretty well with that idea, right? And so it actually is for the segmentation problem, it's actually quite a good method. Back to Pascal. So Pascal was a student at UCLA. He has a very nice paper on image processing online with code that you can download for all of these algorithms, and you can upload your face if you want to, and it will do the Mumford-Cha segmentation and the Chan-Vesse segmentation. And so this is Pascal's face with a piecewise constant and the piecewise smooth representation. So this was kind of where I was coming from. Now, since my background is in nonlinear PDE, I got very interested in some of the under-the-hood math. So some of that math involves taking that that geometric term, the length of the boundary, you can rewrite that minimization problem using characteristic functions. So we can take gamma to be the boundary of some domain, omega. This is a very poor segmentation of the livestock, by the way. And so you take, so now look at u, which is the characteristic function of omega. We can represent the length of the boundary in terms of a functional on u. And so that is well known, and that is the total variation. Okay, so the total variation of u, which is the integral of it's the L1 norm of the gradient of u, is the length of the boundary. So that's the perimeter. So that's a nice idea that has a long history of mathematics associated with it. There's yet another representation which I like as somebody who does nonlinear PDE and I love Sobolev spaces and I love to do energy estimates, don't we all? Okay, all right, so if you like that sort of thing, then you really like this other functional that looks quite different. So this term here is the L2 norm of the gradient, not the L1 norm, and they're vastly different. Because the L1 norm of the gradient allows piecewise, it allows for solutions with jump discontinuities. They're not penalized by this term. This term forces smoothness, so you cannot have those sharp edges with this term. But there's a small parameter. And this term is a double well potential with a large parameter. The double well is forcing you to look like a characteristic function. Okay? And this is called the Ginzburg-Landau energy with epsilon as the parameter. And there is a notion of gamma convergence for which this functional ends up converging to this one here. So they're very related to each other. And why do we like this one? Well, if you like to do numerical methods and you don't like to work too hard at coding things, and back in the day, by the way, if you go back like 10 or 15 years, people were minimizing this functional in the plane by taking the first variation and doing a gradient descent. And you get a very nonlinear PDE. And it's a pain in the neck to simulate that thing. However, if you take this problem and you do the gradient descent of this problem, you get this equation. And that's called the Alenkon equation. Okay? And the first term is our friend. That is the heat equation. And everybody and their other friends have, those who like to compute, have a very efficient solver for that, especially on uniform grids. It's almost trivial now in our world today to solve the heat equation. But it's not the heat equation, actually. It's the heat equation plus this extra term, which is very important because the extra term pushes you, it's what categorizes the solution into one of two categories in this particular case. What's beautiful about the Alencon equation is you get the interfacial dynamics and the limit as epsilon goes to 0. You recover a dynamical problem, which is motion by mean curvature. So if you look at sort of the interfacial boundary between the two wells of the double well in the plane of the solution, right? What you see is that that thing looks like motion by mean curvature. And so this idea led to, this is also stuff from UCLA, led to this beautiful idea by Merriam and Benz-Osher, which we will call MBO, which involves alternating between the heat equation, which is the first part of the Alencon equation, and thresholding. And you might say, well, how do you get thresholding from the double well? Well, if you look at the gradient descent into the double well, you're picking one of the two wells. That's what you're doing. And if you go all the way to the bottom of the well, that is your threshold. All the threshold does is it says, am I closest to this well or this well? And I'm going to pick that one. It's just a threshold function. So that was their idea, that if you alternate between the heat equation and thresholding, and here's how it works. I take a curve. Now I take the characteristic function whose boundary is this curve. I take that as the initial data for the heat equation. I solve the heat equation for a short time. I threshold that solution. I do not get the same curve back again. I get a different curve back. And that's C2. And I do that again. I get C3. And if you follow these curves, they are discrete. They're kind of hopping around. But if you take little time steps, you get effectively a dynamics, which is motion by mean curvature. And that's a beautiful result, and it decreases the length of the boundary. Okay, so all of this and by the way, this idea was taken and then used for image segmentation by two of our former postdocs, Selim Esadoglu and Richard Tsai, and that was published in 2006. So all of this had been done, and I was following some of this, and I was working on my own stuff on in-painting. Carol was involved in some of that work when she was visiting UCLA. And so the idea was that the kinds of things that I've just described to you that are all image segmentation problems in Euclidean space. By the way, when you do the heat equation part, typically people are doing things like pseudospectral methods with a fast Fourier transform, where you have to use all the modes to solve that minimal surface problem. I thought, these ideas we should be using for big data, right? And I didn't know a lot about big data, but I knew that people were using graphs to represent big data. So I had this crazy idea in my head, not knowing a lot about graphs or anything, that we should do that. And so that idea led to a whole body of work. And so this is kind of the parallel now. Instead of solving a minimal surface problem for the length of the curve, we're going to solve a graph minimum cut problem, which is a famous problem in computer science. We're going to use the graph Laplacian instead of the Laplace operator. We're going to project onto eigensubspaces of the graph Laplacian. And then when you get down to this level here, we're going to do pseudospectral, but we're not going to use the fast Fourier transform because that's not what you do with graphs. What you do instead, you use ideas like the Nystrom extension or the Rayleigh-Chebyshev method. And I understand Andrew gave a talk earlier today, and I wasn't here because I was flying in from Los Angeles. So, somebody should tell me to skip if some of this was covered by him. Okay, so weighted graphs for big data. So you have data assigned to nodes on the graph, and you assign weights between the nodes that compare the data that compare pieces of data. So, and there are lots of examples, like the U.S. Congress. Andrew may have talked about that. Or the non-local means graph for image processing, or problems with hyperspectral. So we've been working with hyperspectral data, which is very exciting because it's very high dimensional. So if you want to see how well your code does, that's a good set of data to work on. And here's the beautiful thing, which is that the minimum cut problem, if you want to minimize the cut, so what we're trying to do is we're trying to minimize the sum of the weights between unlike nodes. So you can write that mathematically by taking a function that assigns a value to every node on the graph, and if they have the same value, then they're in the same class. So f is basically our classification function. And so the total variation on the graph is this object here, and it's exactly the size of the cut for the assignment function. This is actually the graph cut problem. It's exactly. I mean, people have said, oh, you're not really solving the graph cut problem. I'm like, yes, I am. We are exactly well, okay. Our goal is to solve this, okay. Okay, so, and so the idea of putting big data on graphs in the imaging context has some nice history going back to Boati's Colin Morel introducing the non-local means graph for images. Now, they did not do TV. Total variation was picked up by Osher and Gilboa around 07, 08, and that had a big impact, also in image processing. There's also been some work on using TV methods for Cheeger cuts, and these are some of the papers. No surprise, a lot of these people are former UCLA postdocs because we like TV at UCLA. And then, okay, so now we get to our work. So this was the crazy idea, and I'll tell you a little bit of the story. I like telling stories because I think that's more important than the details of the math, which anybody can read in the paper. But the story part is cool. I was at China Lake giving a lecture, and China Lake is a naval facility where Arjuna Fenner works, and he's a Navy scientist. And I gave my talk, and I was talking about data and image processing, and Arjuna says, I want to show you something I'm doing. And he said, I'm taking the non-local means graph, I'm using the Nystrom extension to compute eigenfunctions of the graph Laplacian, and I'm solving the heat equation with this. And the results are kind of cool, but I have no idea what to do with it, right? He showed this to me. And he's like, I don't know when to stop it. If I go a part of the way, it looks really good, and then it does something weird, I don't know what to do. And I looked at him, and I said, seriously? He said, yeah. I said, okay, you have to sit and listen to me for 20 minutes and don't say anything. Because I had this idea in my head for like 2 years. I said, we're going to write a paper, I hope. And I just sketched out the algorithm. I said, this is the algorithm. We're going to do Ginzburg-Landau on graphs. And you have the hard part done. It was published in 2012, and 2 years later, we somehow got a prize for it, which is pretty cool. And I have Arjuna to thank, because I was wandering around thinking, I don't have time to figure out this graph stuff. And he had already figured it out and kind of showed me, we worked together on this. So here's the idea. You have the graph Laplacian. So what is the graph Laplacian? So you have the weights, which we've already talked about, minus the weights on the off diagonal. And the diagonal elements are on the diagonal, you have the strength of the node, which is the sum of all the weights coming into that node. And so that is the graph Laplacian. It is very much like the continuous Laplace operator. If you look at finite difference approximations, that's a special case, okay? For the four regular graph in 2D, the grid, just so okay, so now once you have that, you can define an inner product, and this inner product here is called the Dirichlet energy, and it is the analog of the H1 semi-norm for continuous operators in Euclidean space. Now, for practical purposes, people work with different rescalings of the graph Laplacian in real life. So this is a popular one that we make use of, which is a symmetric rescaled graph Laplacian where you rescale by the diagonal. This is the diagonal matrix right here. And then there's a random walk version as well. So I'm not going to go into lots of detail about that, but here is, so we basically took a leap of faith and wrote this thing down. So this is we call this the Ginzburg-Landau on graph, so this is our double well potential right here. This is the Dirichlet energy with a small parameter in front of it. The double well has a big parameter. So this is basically the graph analog of the Ginzburg-Landau energy. And we thought, well, let's try it with the simplest case, which is this is a semi-supervised learning problem. So you have an additional term, which is, again, remember the least squares penalty from the image processing problems for the data. This is the data. So you have some nodes where you actually know what the graph assignment is. And so we're trying to solve for the assignment problem here, what class you're in. And so here's the least squares fit to some of the known classes. And this parameter just tells you which node is a training data and which one isn't. Right? And so that's the model. And so we tried that. And so gradient descent, which is pretty easy to do. a coupled set of ODEs. And now here is where things get interesting. So for big data, you typically don't want to compute this whole thing, because if you're like doing your homework here and paying attention, if I've got n nodes and n is large, then I'm computing n squared weights. So this is where the magic comes in. And this is where, like, Arjuna already figuring out how to use the Nystrom is really helpful. So one of the methods that we use is where we don't actually solve this thing. We actually compute a set of eigenfunctions that are not the full set, right? Because that's too expensive. So we compute like 100 eigenfunctions of the graph Laplacian for problems that might have anywhere from 50,000 to 1 million graph nodes. Okay, so you're not going to compute all the weights, but you can compute a couple hundred eigenfunctions pretty easily using low-rank approximations. So the Nystrom extension is a low-rank approximation of that matrix. And then once you have, so the beautiful thing is, going back to the idea of pseudospectral methods and the Fourier transform for the heat equation, once you have eigenfunctions and eigenvalues, you have your transform. Right? It's maybe a low-rank approximation transform, but it's done, right? It's all done. So that's it. And so the algorithm is very fast and it's very quick. The hard part is getting the eigenfunctions. Once you have that, seconds, a few seconds to minimize this. And so that worked great. And so we had to prove theorems. So the first theorem we proved was with Eve van Gennep. And so the beautiful thing is that not exactly this functional, but a variant of this functional, which is here, we can show gamma converges to the total variation on the graph. This is the graph cut energy right here. This is exactly the graph cut energy. So this theorem tells us that we weren't making a crazy leap of faith. We were actually getting pretty close to solving the actual graph cut problem using a nonlinear model rather than a linear one. So we're not doing literally doing linear approximations here. We're actually trying to solve, with this term, we're trying to solve a fully nonlinear problem. So that was the idea. And it's a geometric problem, right? So that was cool. So that's in this paper. This is in a PDE paper, because that's where I know how to publish. So, right, that's how it is. Okay, so here, simple examples. Andrew may have shown some of these, so I want to get to the fun stuff. Votes. Okay, votes are easy. So we do really well with figuring out the party affiliation of the 1984, by the way. 1984 Congress is a harder problem than today, right? Gee, can we figure out which, how many votes do we need to figure out which party you're in? Like one, right? Threshold 1 vote and you're done, right? Right, so 84 was a little harder, right? So. Yeah, and the cows. Okay, this is another thing. This is another story, anecdotal story. If you write a paper with a new image as your test problem, and the paper goes viral, that image is going to go viral. Think Lena, So we have our version of Lena, which is the cows. It's not as viral as Lena, right? The cows have we're talking, about maybe 30 or 40 or 50 papers with the cows now, not like thousands, but... That's a fun story. I love telling stories. So Arjuna said to me, I have to get the paper approved by China Lake, and they're going to want to make sure there's no classified or ITAR information in that thing. So I have to pick an image that they're just not even going to think about, right? So he picked this one. He wanted to show image labeling, that we could label the cows in one image and automatically find them in another image. That was to show that we were doing something that was much harder than the original non-local means. This is using the non-local means graph. So it's a big graph. Every pixel is a node, and the feature vector for each node is a patch neighborhood around that pixel. So it's redundant information about the image, but it's organized in such a way that you can get a lot of information. You can do texture matching, for example, using non-local means. The basic idea is using something called convex splitting, which Carol and I kind of wrote the book on, right, for higher order PDE problems in image processing, right? She wrote the book and we wrote a paper, right? So anyway, that's Carol. So the idea is you have an energy with these are non-convex energies typically. So you have a convex and a concave part, And the idea is you split the energy into by the way, there's no like one way to do this, right? You can always add a convex part here and subtract it here, right? So you have to pick an appropriate splitting, and then the idea is when you do the gradient descent, you take a time step, and here's the gradient part, and the convex part has the new time level, and the concave part has the old time level, and that. If you do that right, it's an unconditionally stable scheme, which is very nice. So you can take relatively large time steps, which is good. And so for our problem, this part, the implicit part, is where we project onto the eigenfunctions of the graph Laplacian operator. So that's where we get into like the pseudospectral idea. And so you want to have the spectrum of that operator to be able to do that step. Right? So this is implicit, which means that we'd like to be able to diagonalize this problem. And the way you do it is you project onto these eigenfunctions. Right? And that projection, which is easy to do because you just take inner products, right? You're just taking inner products. And so that projection diagonalizes this operator. Okay. So now, once that was done, the obvious next thing to do, based on what I've told you from the historical literature, is to take the MBO scheme and see if we can do MBO for the graph segmentation problem. And it turns out that works beautifully, and that was work done by my former PhD students, Katerina Merkuriev and Tiana Kostic. And it's very simple. So you have this is basically the graph heat equation here. Here's a symmetric graph Laplacian as one example. This term comes from the fitting, the training data. So this is semi-supervised in this example. And here's the thresholding sub. And this is just for binary, but you can generalize this very easily to multi-class. So that's that work from 2013. The algorithm is very straightforward. And all the muscle is in the linear algebra, essentially, which is kind of true for PDEs in general. Okay, so you can do the easy examples like the two moons. You can do the cows. We can do more cows. And then you can get into the so this is like the full powerful method, which is, you want to do general multi-class segmentation. So to do the big problem, we had to get more people involved. So Arjuna, right? Christina Garcia, who was a student working with Alon Perkis at the time at CGU. So she was just down the street from us. I mean, in LA terms, right? She's like an hour and a half drive away, but that's sort of down the street, right? And so, and Katerina and Arjuna, we felt this was such an important problem because most classification problems are not binary, they're multi-class. And yes, you can do recursive binary partitions, but that's really special. You want to be able to throw like 4 classes at a problem and just boom, solve it. Or 5 classes, which 5 classes, right? And so MNIST, we like nailed MNIST. I mean, everyone nails MNIST, but we really nailed MNIST, right? So in this paper we had, here are the results, yeah. So yeah, this is just to show off that we nailed MNIST. So I like to tell people that we're getting close to 97% correct. And you may say, well, other people do even better than that, but other people are using a lot of the data set as training, right? So the supervised methods will use 60, okay, in case you don't know what MNIST is, 70,000 handwritten digits, 10 digits, right? As far as I can, it's still 10, right? So 70,000 handwritten digits. So you can use 60,000 digits as training data and figure out the other 10,000. That doesn't seem like such a hard problem to me. We use 3.6% of the data as training, which is a tiny fraction of the data. So we're really relying on that graph cut to get the right answer for us. We need that. If we don't have that, we're toast. These are our results using a tiny amount of training data. So that's basically the moral of the story, is when you put in the geometry of the structure of the graph, then you suddenly don't need much training. Here's a cool problem that you can solve with this. This is hyperspectral video. So it's an image taken in the desert in Utah with a camera that measures long-wave infrared, and every pixel has 128 dimensions, right? So that's a very high-dimensional pixel, and there are, so here's an example with 4 frames of a video, and we have about 280,000 pixels, in all of those 4 frames. And what we would like to do is we would like to get this result, which is our result, which we're trying to track a gas plume as it moves across the desert. And this is the mountain in the background, the sky in the foreground. So, and this looks very, for people who know this data set, because there's a lot of people in the government who've worked with this data set, this is a wonderful result. And we get it by doing the following steps. We take all the pixels and we do pairwise comparisons to construct a graph using the spectral angle. So cosine angle is how we measure the weight. Instead, we use the Nystrom extension to compute 100 eigenfunctions of the graph Laplacian, along with the eigenvalues. By the way, this is another anecdotal story. We had 3 weeks to see if we could write a paper for ISIB, for an invited symposium. And I said to Katerina, I said, we got to see if we can get something good with the plume data. And she said, I haven't even looked at that. I said, well, try it. Just take your code and just try it. And she said, well, I don't have ground truth. And I said, true. I said, why don't you make up something for ground truth, right? Just make something up. So she said, okay. So she looked at the eigenfunctions. She said, oh, I can threshold these and get some pixels that I'm going to declare as ground truth, right? So she thresholded like this one, this eigenfunction, and came up with the orange pixels for the plume. She thresholded this eigenfunction and came up with the blue pixels for the sky. And so, like in here, the red ones turned into the green pixels for the mountain, and so on and so forth. So this set of 4 frames shows you her fake ground truth, okay? That's how she did it. But there's a lot of white pixels where we don't know what's in, where they go, right? We need to figure out all the white pixels. So then she takes random assignments for the white pixels and gets this as the initial data. She runs the MBO scheme for just a few iterations, and this is what she got. And she shows me this, and I said, okay, we're writing the paper, right? So we wrote the paper in like 2 weeks, and yeah, so that was, right, and we went to Paris. Right, that's how you go to Paris, right? So that was fun. So Justin was a master's student from Long Beach who spent the summer with us developing the Nystrom code on MATLAB. And so he did that calculation. So that was his specialty. So it's nice to have somebody who knows that piece of the problem really well. So in case you're wondering, well, surely can't you do this with simpler methods like k-means? And the answer is no. So k-means cuts the plume in half. Spectral clustering gives you weird effects in the sky, but you get the plume at least. So spectral clustering is pretty close to what we're doing. Spectral clustering involves computing so we use the same eigenfunctions here. Spectral clustering, you compute a few eigenfunctions of the graph Laplacian and then do k-means on the eigenfunctions. You're basically taking the linear information and then kind of massaging it a little bit rather than using it to solve a fully nonlinear problem. But it's an interesting idea, and it's very cheap once you have the eigenfunctions. Okay, so we decided to go crazy and try the Chan-Vessey method on the graph, because that's an unsupervised method, right? There's no training data. You can do that without training data. You still get the plume, but sometimes you don't do as well as other times. So this is very non-convex, and you get kind of different results depending on your initial conditions. But still, you can get some very nice results for the unsupervised problem. And that's work by my student Hui, who's at Google now, and Justin, who's a PhD student at CGU. So you can also look at other hyperspectral data, like the classic urban problem. This is actually published now. So we have some code. If you want to try this, we have code on the IPOL server, Image Processing Online, in France. That will solve your favorite hyperspectral clustering problem using either of these methods that I'm talking about. So that's this paper here. Okay, so once we felt that we had a method that was very powerful for larger graphs, we had to go crazy and try a graph with 13 million nodes. But you can't do that on a laptop because of memory issues. So we took this problem to the National Energy Research Supercomputing Center, NERSC, at Lawrence Berkeley National Lab. And I have a colleague there, Alice Conegus, who had my student, Gloria, work with her for almost a year, developing this code to run on this this big supercomputer called Cori. It's one of the fastest machines in the country. It's one of the biggest machines in the country. And one of the things we did was we took the original Nystrom code, which is here, and these are the two pieces of the Nystrom right here, and the rest of it is, this is the MBO scheme on the graph. And you can see how much we've shrunken the runtime for the original Nystrom. And then this is just showing that we get good parallel scaling, using more threads on the supercomputer. So this will run in, using the full power of the supercomputer, we can do 13 million graph nodes of the hyperspectral video. So every node has 128 dimensions. We're running Nystrom to compute graph Laplacians, 13 million nodes. It runs in like 2 seconds on Cori. Cori just sort of sneezed at it and went on to doing other things. So I guess what I'm telling you is that once you have a supercomputer, you can just go crazy with this stuff, right? I mean this problem just barely scratched the surface of what the supercomputer can do. So once I started telling people that we had a cool thing for graphs that could deal with big graphs, I started looking for, you have a hammer, right? You want nails? And so I was looking for nails, and so Mason Porter showed up from Oxford and said, well, you ought to try this thing called modularity optimization. I said, what's that? He said, well, it's this crazy thing that physicists do, right? There's a paper going all the way back to 2004 by Newman and Gervan that, so here it is right here. So it's this function that measures the fraction of the total. So it's a function that measures optimality of partitions of a network. So G is the assignment the assignment of each of the nodes to some class. So it's a class assignment, and given a particular class assignment, you compute this thing called the modularity, and then you try to maximize that. So it measures the fraction of the total edge weights within each community or assignment minus the edge weight expected if the edges were placed randomly using some null model. And the null model that a lot of people use is from this Newman and Gervan paper right here. And these are just all the graph. So the W are the weights. The degree of the nodes is Ki. That's the diagonal on the graph Laplacian right there. And then this Pij is this function here, and M is just the mass of the graph. So that's it. And so, you can compute the modularity for any partition. The hard part is optimizing modularity. And there have been, it's an NP hard problem. There's several thousand papers in the literature, I believe, that cite this original paper. And by the way, all of this is in the statistical physics literature with only very modest overlap to the machine learning literature. So, the first thing we did was we looked at that and said, oh, I wonder if you can use that for machine learning. And Mason said, oh no, it's too hard. So we thought, well, let's try it, right? The code ran for 2 days. Okay, so we're sitting there waiting for 2 days. The results come out, and they are perfect, right? It totally, it gets everything, right? It does a perfect job. Yeah. So since it worked really well, we knew that the problem wasn't whether modularity was a good idea, but the problem was it was too slow, right? And the beautiful thing about the modularity functional, and I'm just going to cut to the chase, is that maximizing modularity, and this is what we showed in our paper, is actually equivalent to minimizing a variant of the graph TV functional. So it is graph TV minus this term, which is sort of a least. This is kind of a second moment term, and this is the assignment function here. So you have this term. So it's non-convex, and you have this term here. But anyway, it looks a lot like problems that we were trying to solve already. So we said, well, maybe we can do that with MBO. So sure enough, it works great, right? You can actually do it, and it works great. And I don't think the network people were that impressed because we were getting the same answers that they were getting already, just maybe a little bit faster. Here's a toy problem, the 2-moon data set. So with 2 moons, you want to know how many moons are there and what's the segmentation, right? So we compute the optimal modularity. So what we do is we fix the number. So actually, I have to go back and explain this better. For a fixed number of classes, this is true, right? If you fix the number of classes, which we don't know. So here's what we do. We try one class, that's boring. We try 2 classes. So this is the optimal modularity with 2 classes based on our code. 3 classes, 4 classes. And then you look at the solutions and you see that the maximum modularity over all these classes that we tried is this one, which is n equals 2, and that's the partition. Which looks pretty good. So we tried 3-point clouds. And again, you try different numbers of classes, and that's the maximum modularity, and that's the partition. That looks pretty good, but these are really toy problems. If it doesn't get these right, you just throw the idea away, right? Okay, let's go crazy. Let's try MNIST, right? Let's try 70,000 digits. No, well, we tried, okay, so we did the 2 and the 4 first, which is 2 classes. And that did quite well, but we decided to really push the envelope and try 70,000 digits of MNIST. And we used the local rescaling graph, the Zelnick, Manor, Perona version in their paper. We used their graph. And you can take the Jen-Louvain code, which is Peter Mucka's code, and just feed it the graph. You can feed it the Zelnick, Manor, Perona graph and ask what the optimal modularity is and what the partition is. And it will take several hours to run. And it will tell you that there are 11 classes in MNIST, and it gets it right with about 97% accuracy. And you might be thinking, okay, so the extra class is the 3%? And the answer is no. The extra class is actually the ones broken into the sticks and the ones with the flag. Actually, we're counting that as the correct answer, right? We're saying, okay, well, you can have 11 classes as long as you're just breaking it up correctly. So that worked really well, but that is not good, right? The several hours for a moderately sized machine learning problem is no good. So our code is running in a couple of minutes, and it's getting pretty darn close to the Jen-Louvain answer, and it's getting the same 11 classes. Here we tried 2 to 20. So there's a little bit of a catch here, which is that we're making an educated guess as to how many classes there are. So we're not assuming exactly 10 classes. Well, we did that too. When we assume there's exactly 10 classes, we get this answer, which is also quite good and faster. But you can also assume that you don't know how many classes there are, but try a bunch of educated guesses. And so that's what we did here. And you can see the runtime is it's orders of magnitude faster than Jen-Louvain. So that was the big win for this paper, which came out a few years ago in SciAm. And so, all right, so I'll just say that there are benchmarks that people do in the networks literature, like the Lfr Benchmark, which is named after these guys. There are too many syllables to pronounce, but those guys, right? Lfr. So our code does okay, but it's probably not, it does okay so Lfr creates these horrible graphs, right, where you can have mixtures between classes. There's synthetic. And for the really nasty, horrible ones that you have no business segmenting anyway, our code doesn't do that well. But on the networks that are kind of more normal networks, our code is kind of comparable to, here's a mixing parameter. So below about a half, we're holding our own, and then up in this range, so Jen-Louvain is kind of beating everyone else, but this is also the range where you're working with like garbage networks. Okay, so so my student, let me just mention that for those of you who are thinking in your heads, these are all local energy minimizer problems. You're looking at non-convex functionals. You're not necessarily finding the optimal solution. That's true. A lot of the times we are, but sometimes we're not. So one of the things we did do is we worked through how do you design a scheme that will guarantee an optimal solution. We did this in the 2-class case. And we had to come up with a completely new scheme, which is sort of built on more classical TV methods, like the max flow, which is already used for graph cuts, and primal augmented Lagrangian. So the upshot is that they're much more expensive and time-consuming than MBO. But for this type of problem, semi-supervised 2-class, we can guarantee that you will get the global minimizer for those problems. And we have a proof. We have a theorem. Okay, so really cool applications. So we're having fun with body-worn video cameras. Actually, we're not wearing them, which would be more fun, actually, than what we are doing. So what we're doing is we're working with the Los Angeles Police Department. So you might be aware of the fact that a lot of police departments, like in the last couple of years, are transitioning into having their entire patrol force wearing cameras, right, on their uniforms. In particular, when they get out of the patrol car, as soon as they start doing anything interacting with people, they have to turn it on. This is how it is in Los Angeles. And so all of this data is being collected, and there's just terabytes of it, and it's sitting there. My student Gloria went to Paris for fall quarter last year to work with Jean-Michel Morel. To try to learn some of the stuff that they were doing with ego motion. And so the basic idea is you take the full video and you want to boil it down to a very low dimensional vector to describe the ego motion. And that's pretty easy to do with fairly standard image processing techniques where you're looking at the movement of the signal in 4 directions. So the 4 directions, you might think there's only 3 directions. It's true. So there's the 3 spatial coordinates. But then there's also rotation, so we're counting that as one of the directions. And then you can take the frequency of those motions. Like if you're running, your time frequency is different from if you're walking, right? So you take that information too. And so we have lots of ways we do that. That's part of the under the hood. But you get an 8-dimensional feature vector. And then the question is, can we segment the video? So here is a video that's not from the police. It's a video you can download from the internet. It's a test video that has, they have 9 different classes of motion, and they do a repeated, they do 4 trials of those 9 classes. So you know what you have ground truth. And so we tried to see if we could, just by using the 8-dimensional feature vector, segment the video. And so the best of all the codes we tried this basic k-means, we tried the unsupervised MBO, and we tried semi-supervised MBO with 10% training data. This is the one. This one did the best of all of them, and you can see, so this is the time axis, and you can see a color code of the different actions in the video, and you can see semi-supervised is matching the ground truth quite well. So, and this is with, the training data is taken from the video itself, which makes it easier to do. But it's still pretty hard. We're doing pretty well with that. So semi-supervised MBO is this axis here for different motions. So somewhere north or south of 90% correct with 10% training data. Oh yeah. So you know what? I got my slides out of order. Let me see. There we go. So over the summer, I got a bunch. So one of the problems with the police videos is that they're not hand classified, so we have no official ground truth. So I do run an undergraduate RU. So we basically got 4 RU students and said that wouldn't it be fun to watch hours of police videos and hand classify what the actions they're doing are, and then you could do machine learning on it to see, right? And so so if you divide and conquer and you have enough pairs of hands, you can. So we now have a big data set from LAPD that we have hand classified. So another issue with doing this kind of work is that with a data set like this, it's very sensitive. We cannot put the data set on any machine that's connected to the internet. It can't be in a room, it has to be in a lockdown machine in a lockdown room. There's a lot of privacy issues, which makes it pretty hard to develop code on the data set itself. That's why this 8-dimensional reduction was so helpful, because you can take the 8-dimensional, the code that gives you the 8 dimensions is pretty easy. You can just stick it on the lockdown computer, run that code, and generate those feature vectors for all the videos, and then you can pull the feature vectors off, and they're anonymized. Right? The police could care less what we do with the feature vectors, right? And then you can play with the algorithms on the regular machine. So that's what we did. So over the summer, last summer, I had my students. So then, once they had done the hand classification, we let them play with the algorithms. And so this is kind of where we are. So we have a bunch of different trials that we've done. You can see these are some of the classes that we had that they hand classified, right? So standing, in the stationary car, on a bike, walking, entering, exiting with passengers. So just to give you an idea, they actually looked at 4.86 hours of video, right? And that's like about 500,000 frames, over 500,000 frames, over 40 videos. They came up, I think we're up to 60 videos now that we've looked at. So this is old data, old results. We're writing a paper now. This 10% fidelity seems to be a bit of a magic number for us. That seems to be a good number for us. Yeah, so the results with this, using MBO on graphs with this number of classes, the results are quite good. Where you have problems are things like where you have very little, if you have very little data in certain classes, so the balance is not so good between different classes. So the blue lines are the original data set and the results we get. And you can see that the ones that have like lower accuracy, like enter driver, where's enter driver? Enter driver has almost no data, right? So we shouldn't really be able to do very well. So we thought we'd cheat and see, we wanted to test the effect of the size of the populations on the algorithm, right? So what we did was we took these classes that had very little and we just literally copied the video, like the frames, and we made multiple copies of the same frames or the same feature vectors and added them to the data set that we were trying to segment. And that's the orange. So the orange data is the incremented data. It's the same data, but where we add extra frames of these. And suddenly, these numbers shoot, except for obscure camera. I'm not sure why obscure camera got worse. But all of these, we get much, much better results in the classification. And we don't have to make them all equal. We just have to give them a boost that gets closer to the same order of magnitude as the big classes. I'll just say we get papers, lots of papers, and lots of fun things. And several of my colleagues here, Carola has been working in this area, and Andrew Stewart has doing some really nice work. I didn't show his slide because I think he just gave a talk on that whole problem, right? So uncertainty quantification. So thank you.